So here we've got a seesaw where we've got a boy of mass 45 kilograms on one end, and on the other end, 3 meters away from the center, is another boy of mass 35 kilograms. Now clearly this is an unbalanced situation if the distance from that little pivot point at the middle is the same for each boy, and this thing is going to start to rotate counterclockwise. So the question is, we want to get this girl to sit on the seesaw somewhere to prevent it from rotating. So we want this thing to get into rotational equilibrium, which simply means the sum of the torques has to equal 0. So we're looking for the following condition. We want to achieve rotational equilibrium. We want the sum of all the torques acting on that beam, on that seesaw, to add up to 0. Now torques are a vector. They're a rotational vector. They can either be clockwise or counterclockwise. So this little statement simply means the torques have to be balanced. So I prefer to do it this way. The sum of all the torques causing this system to spin clockwise has to add up to all the torques causing the system to spin counterclockwise. I just find that a little bit easier to understand. So there's my condition. Now, it's also because it's in static equilibrium, it's also not accelerating. The whole system is stationary, so the acceleration is 0. So we say that static equilibrium satisfies two things. It satisfies the rotational equilibrium condition that we just talked about, but it also satisfies our translational equilibrium, which simply says that the sum of all the forces acting on that system have to add up to 0 as well. Now, torque is force times distance, so the location of the force matters, but translational equilibrium, it doesn't matter. We just have to have all the forces balanced for translational equilibrium. So we'll return to that in a second. So since we're dealing with forces and distances, let's start by finishing our diagram in terms of our free body diagram. Now, we want the forces that are acting on the object in question, which is the seesaw. So what are the forces acting directly on the seesaw? I'll use blue so we can see them. Well, the boy A here is exerting a force straight down on the seesaw. So I'll call that force of gravity A. Same with boy B, a little bit less, straight down, force of gravity B. Now it makes sense that the girl is going to have to be on the right-hand side somewhere. So somewhere in this region here, our girl is going to have to sit, and she's going to exert a force of gravity down as well. Force of gravity C. So I've got 3 downward forces. Now if that was it, this object would fall, right? All my forces are directed downward. There has to be one force that's countering it. And if you look, and I remember, all I care about are the forces acting on the beam. The rock, or the fulcrum, is holding the whole thing up. So there's an upward force, kind of a normal force, between the beam and the rock. I'll just call it force up. Now this one, for now, is unknown. All these other forces of gravity I can calculate. 45 times 9.8, 25 times 9.8, 35 times 9.8. The force up, I don't really know at this stage. So a little trick when you're doing static equilibrium questions or rotational equilibrium questions, if we are in a situation where it's not spinning, you want to pick your pivot point, because you're allowed to pick your pivot point anywhere you like. You want to pick it at a location where you don't know the force. So, for example, I don't know force up at this stage, and I don't want to calculate it. So let's make that my pivot point, which it is anyway. I mean, that's where the rock is. But I want to use that as my pivot point because that means that this force is exerting 0 torques on that point. Remember, torque is force times distance to the chosen pivot. So if I choose this location as my pivot point, any force that's 0 distance away will not exert a torque. So I'm allowed to pick it anywhere I like. I'm going to choose a spot to wipe out an unknown force. So I don't know that value. So there's my pivot point. All my distances must be from that pivot point. So let's go for it now. The sum of the torques that are clockwise has to equal the sum of the torques that are counterclockwise. Well, what do I have for clockwise? Well, if you look here, girl C is causing it to spin this way. The buoy B is causing it to spin this way, and buoy A is causing it to spin the other way. So I've got 2 clockwise torques and 1 counterclockwise torque. So let's go ahead and write our equation. Torque is force times distance. So it's force of gravity C times the distance to the pivot point, which in this case is what we're trying to figure out, X. Now you always want to make sure that the force and the distance are perpendicular to each other, and they absolutely are. Here's my force, my distance is right angles to it. That's good, that's creating a torque. Plus force of gravity B from the buoy on the edge times his distance to the pivot point, which they tell you in the question is 3 meters. Equals, and again, they're 90 degrees, the distance and the force, so we're good. Equals force of gravity A and times the distance to the pivot point, which is also 3 meters. So there's my equation. Now, if we go through it, we know how to calculate force of gravity. This will just be mass of the girl, which we're calling mass C, times G times X, plus mass B times G times 3 equals mass A times G times 3. Now you could work out all those forces and just put them in directly into the equation where you see mg. The reason I've done it this way is because it tells us just a little bit more. If you look at it, there's a g in every single expression. I could factor a g out on the left and it would cancel with this 1g on the right. So all the g's cancel, which is interesting because that simply means that this result, when we're solving for x, is valid on any planet. G does not actually matter in this particular case. So now we go ahead and solve it for x, and basically we get an equation that looks like this. Mass C, 25 times x, plus mass B, 35 times 3 equals mass A, 45 times 3. Isolate x, and you get x is 1.2 meters from the center. Remember, the distance is always from our chosen pivot point, so we chose the center as our pivot point. Now, if I want to figure out the value for this force up, if I want to figure out what that is, let's go to our other condition. We know the object is not accelerating. So if I use my translational equilibrium condition, that means all the forces have to be balanced. So let's go through that. I'll use yellow again. So forces up have to equal forces down. That's what this system means. So force up has to equal force down. Now force up is what we're trying to figure out. And force down are the 3 forces of gravity. FGA plus FGB, doesn't matter what order, plus FGC. Now I can work all of those out fairly easily. They're all just m times 9.8. So 45 times 9.8 plus 25 times 9.8 plus 35 times 9.8, etc. And I end up getting a force in the upward direction of 1,029 newtons. Now that will simply be 45 plus 25 plus 35, which is 105 kilograms times 9.8. So it's this equation, and I just plugged in my values.